Deshmukh here with us, coming across town from UCSB, where he works as a professor of environmental studies and with the Bren School there. So Dr. Deshmukh is actually an engineer by training, got his bachelor's in engineering from the Government College of Engineering in India, and then master's degrees from both Humboldt State and University of Texas at Austin. And done a lot of traveling, because then got his PhD at UC Berkeley and did a postdoc in, where is the Lawrence Berkeley National Lab?
It's right next to UC Berkeley.
Oh, well, so didn't go too far for that.
Yeah.
But then he came down here in 2019 to join the faculty at UCSB. So he's an engineer by training, but is very much pursuing interdisciplinary questions now, which he'll be talking about today regarding energy and energy policy. And even some environmental justice issues in there, I believe. So thanks so much for joining us.
Thank you. Great. How's everyone doing? Good. All right. Yeah. So I'm going to talk about low carbon transitions, and that's what I work on. Let me know if the audio doesn't come through, if I digress from the mic a bit. But there's, there are some plots in there, some data, but I'm going to walk you through that. And it's more important to just understand the stories and how we basically approach problems to understand low carbon transitions in different settings. Sounds good? Ready for the journey? All right. As soon as I get my pointer to work, let's see. My pointer doesn't work. That's all right. Okay, so this is my research lab. Some of the students, of course, have graduated. But I run a lab called the Clean Energy Transformation Lab on campus. It's called SET Lab, where we have undergrads, grads, postdocs working on different research questions and in different parts of the world. And then I'm also part of another lab, which is a much larger lab with many different faculty members, and that's called the Environmental Markets Lab. And it's mainly dominated by economists, and we look at how policies affect mainly energy transitions, but also poverty, fisheries, and whatnot. And then the last affiliation that I have on campus is called the Institute for Energy Efficiency. And again, it's a whole bunch of faculty, a new building, and people work on really cool things like machine learning and lasers and LED lights, and we have at least one Nobel Prize winner who invented the LED light bulb, which is really cool. So if you come visit UC Santa Barbara, you can check out these labs. Yeah? So just to give you a sort of high level, just to set the context, right? And you know most of these facts. We know climate change is happening, right? Has anybody seen this kind of plot before? Yeah? Okay. So what do we see here? We see a few pathways, right? We are somewhere on this black line near 2020. And then what it shows is how our GHG emissions are going to change, right? And then what pathways it's going to take, and what kind of temperatures we're going to see by the year 2100, right? To keep sort of climate change impacts at an acceptable sort of level, there's never an acceptable level, right? You all are from Westmont. You have, were you guys here during the Thomas Fire and the mudslides? Anybody here? Okay, so yeah, a crazy time, right? I mean, is climate change responsible for those fires? Maybe, maybe not, right? We don't know. But we do know that when fires happen, they're burning warmer, our forests are getting drier, right? So climate change is having impacts. It's worsening impacts that we are already seeing from these fires and mudslides and precipitation events. So we have to reduce our emissions, our annual emissions, down to a really low level to keep temperatures in acceptable ranges. So that's what this plot is showing. Here's actually a picture from Montecito, by the way. Okay. But at the same time, it's not just GHG emissions from our transportation sector, our cars, our power plants. It's the local emissions that are also being emitted from these, from burning fossil fuels. This is a picture from Delhi, huge air pollution. If you go to LA, back in the 70s, it was really worse. But now it's again getting bad because there's just so many cars. Even if we have a lot of pollution control systems on our cars, the air can get really bad, right? Who's from LA? Right? It's pretty bad, right? Oh no, yeah. And it's not just the air, the water can be polluted because of fossil fuels, and there's a host of really bad pollution events that happen because of these. And then lastly, I want to remind you that we may be thinking about decarbonizing our energy systems. We all have cars, or many of us do. We have electricity 24/7, or at least almost 24/7. But about 1 billion people don't have access to electricity. So the challenge in front of us is like, how do we provide electricity access, amenities? The world is going to heat up. How do we provide air conditioning, cooling, etc., but also keep our emissions to a really low level? How do we reduce those emissions? That's the challenge in front of us, and it's huge, right? So we work at basically asking those particular research questions. How do we mitigate our carbon emissions? And then at the same time, how do we mitigate the local emissions, but also having this whole energy transition be equitable? And what does that mean? In one of the research projects that I'm going to share today, I'll explain more about what energy justice and equity means here, or how we can tackle that. But one example is that 1 billion people don't have access to electricity, right? That's an energy justice issue. But here at home, we also know that some fossil fuel plants are in communities, and those are the communities that are facing the brunt of air pollution, right? Or water pollution. They're experiencing more cancer rates, right? So as we transition, how do we make sure that these inequities are not exacerbated? How do we provide more access to electric car chargers in communities that don't have access? They have less public parking, less public chargers. So there's a host of questions that we need to answer, okay? One thing I forgot to mention is that just please ask me questions anytime during my presentation. I would love for it to be interactive. That's what makes it fun, right? Is that okay? All right, don't be shy. Okay, so that's the doom and gloom, right? But I want to show you at least some promising changes that have happened over the last couple of decades. One is energy efficient technologies, LED lights, right? Now, wherever you look at, I mean, all these are probably LED lights. Maybe some of them are CFLs. But LED lights have cut down our electricity consumption significantly. We had those, I don't know, you guys are pretty young, so do you remember those incandescent lights, right? They're still used in some places for ambiance, but in general, like, we don't see those anymore, right? And those, if you touch a light, it gets really hot, right? Why is it hot? Because those are essentially electricity losses. That's why it makes it so inefficient, because its main function is light, but it was just creating heat. And that's why it's so hot to touch those incandescent lights. But if you touch an LED light, it's like it's not going to release all that heat. So these are really efficient technologies for lighting as well as our televisions. Has anybody seen a CRT, a cathode ray tubes television? How old are you? I'm just kidding. Those are big boxes, right? They're super inefficient. But I grew up with those, and those are just terrible in terms of their electricity consumption. Second big change, the costs of wind and solar. So here in this plot, on the y-axis, we have the cost of these technologies in terms of electricity generation. And on the x-axis, it's just years. So this goes on until 2020. The orange line is solar, and then the blue line is wind. So you can see how quickly those costs are decreasing. And that is really promising, right? So we have these options now to replace coal as well as natural gas electricity, these fossil fuel generation technologies. Third big change, battery technologies. Wind and solar are weather dependent, right? Some people call them intermittent. We call them variable, weather dependent. But we need electricity 24/7. So how do we make sure that wind and solar can provide that electricity? We need some storage. And luckily, the cost of electric battery storage devices has come down again significantly. So we are installing more and more, especially here in California. We are at the leading edge of these technologies. And then lastly, electric vehicles. Does anybody have an EV? Yeah. Why did you buy an EV?
My parents bought it because we have solar panels.
Because you have solar panels, right? So you want to make use of that electricity. But they are also really cool to drive, right? Way better. They're way faster and way cleaner, right? So the idea to basically 3 approaches to mitigate GHG emissions from the energy sector. And the energy sector by far is the largest emitter of greenhouse gas emissions, okay? About 80 to 90% of our emissions is coming from this sector. So the 3 main approaches, first one is energy efficiency. You want to do a lot more with as little as possible in terms of energy. The second is you decarbonize your electricity generation using wind, solar, maybe some hydro, maybe some nuclear. And the last thing is you want to electrify end uses. So you can use as much clean electricity as possible. So that's where electric vehicles come into place. There's also a lot of industrial end uses that we can electrify and use that clean energy. Okay?
I have a question.
Yeah.
Is there a leading cause what maybe produces the most CO2 or is polluting the most? Is it like an aggregate of a bunch of small things, or is there something big that produces the most?
So the question is, what produces the most CO2?
Yeah, like let's say that you're able to cut down on like each house by 50% of energy consumption in the grand scheme of things. Is that going to make that much of a difference?
So in terms of CO2 emissions, so coal electricity is the worst from electricity sort of generation, yeah? So right now, the US has, how much does it have? Like 20 to 30% electricity coming from coal now, or maybe a little bit more. A lot of it is natural gas. So natural gas is also producing a lot of emissions. But now for the US, in its total economy, about 15 to 20% emissions come from the electricity sector, I believe. But then a huge chunk comes from transportation. I think 35%, maybe 35%. For California, it's 40% comes from transportation. But imagine like all of that goes to EVs, you generate a lot of electricity using wind and solar, and that whole chunk gets decarbonized.
Yeah.
Does that make sense?
Yeah.
And then the rest of it is like industry and whatnot. And a big chunk is, as I will show from one of my slides, 11% comes from refining and just extraction of oil. So 51% comes from the transportation sector, extraction of oil, refining of oil, and burning in your cars. So if everybody sort of transfers, or changes from fossil fuel car to EVs, like that's the change that you're going to see. Does that answer your question?
Yeah.
Okay. Other questions? Okay. So a couple of challenges that we work on in my lab. One is, let's say we want to do a lot of wind and solar here, right? But there are trade-offs because wind and solar do take a lot of land, right? So if you look at this big solar plant in the middle of the desert, people think that there's nothing in the desert, but there are desert tortoises, there's a lot of flora and fauna that could be displaced. And the amount of land that we need, especially for solar, let's say 50% of our California's energy comes from solar. That will mean almost as much land as Santa Barbara County that we would need to cover to provide that energy. So where we put those solar plants is important in terms of mitigating biodiversity impacts, social impacts, etc. Similarly for wind, oftentimes wind resources are at the top of ridges where there's perhaps a lot of forested land. This is one place, not in the US, but there was a lot of deforestation right on the ridges to put up wind plants. Is that the best place? We don't know, right? Wind turbines can also kill a lot of birds, a lot of bats. So you want to make sure that they're not sited as an SITED, in places that have, that are bird migratory paths or where there are a lot of bats, right? And then there's a lot of transmission that is required to connect all these different plants to where you need electricity, as in your homes, your college, etc. So what we've done is we do a lot of GIS analysis. Have you guys heard of GIS? Spatial analysis, yes? If not, then I'm going to explain it. Who has heard of GIS? Okay, only a few people, right? So what is GIS analysis? It's a bunch of maps, right, that you can use to then say, okay, there's a map of just forests, or let's say land use, where every pixel tells you whether it's a forested area or a farmland or a water body or a desert, etc. So think about it like a pixel of maps, pixels on a map. And then you put another map on it. You say, okay, where are the best wind resources? It's again pixelated, okay? So maybe some areas have a lot of sort of wind, like really high wind speeds. In other places, there is not. Then you put another map on that, say, okay, where's the best solar radiation? Because some places, have really great solar radiation, like the Mojave Desert. Other places, not as much. Maybe it's cloudy. Then you might want to put another map with roads, another map with transmission lines, because you want to situate your plants that are closest to transmission lines, right? Or closest to roads, right? To minimize that cost. So you look at all these different layers, and if you look from the top, then you say, okay, which pixel is the best one to set up my solar plant or my wind plant? You might also have a map with pixels that say these particular areas are the really high biodiversity value. We have endangered species there. We want to avoid those. So even if you have really high wind speeds, you want to avoid those areas, right? So think about it like a big sandwich, and then you're only going to choose the pixels that are the most suitable, the closest to transmission lines, the closest to the roads, the best wind speeds, doesn't have biodiversity impacts or social impacts. And that's how we create these maps, to find the best resources. And why is that important? You can direct your project developers to those particular regions. Now one would say, hey, this is a capitalist country, like why should anybody listen to you, right? But there's always a back and forth between project developers and our policy planners. Why is that? Because the project developer is going to just set up their wind turbines, but they still need a transmission line to connect it, right? So then we need planners that do such an exercise to plan their transmission lines first. Transmission lines take about at least 5 to 10 years to build. A wind plant or a solar plant can go up in just about a year. So you want to plan your transmission lines beforehand. So that's why these planning exercises are so important. Now, not everybody does such a comprehensive planning. California has started to do it. But we do this analysis, we've done it across the world now. Our first project was in Eastern and Southern Africa. That's why you see a chunk of Africa gone, which is the west side. But this project had only the Eastern and Western Africa here. So I'm just illustrating what we did here. We call it a geospatial renewable resource assessment, which is what I just explained. But what we did after that analysis, we came up with what we call renewable energy zones. So these are large large areas where you want project developers to go and install different wind and solar power plants, okay? This is a map of Kenya on the right. And then we also came up with a whole bunch of different economic and non-economic criteria. So what is the economic criteria? It's the cost. How much would it cost to generate electricity from a wind plant or from a solar plant? It's called levelized cost of energy. We also estimated the cost for extending a transmission line and extending a road to the nearest road infrastructure. And then these non-economic criteria, are, proximity to a city, or an environmental impact score, or what we call a capacity value, as in how well that wind generation is going to match your demand, because the more it matches, the better it is. If the wind is just blowing in the middle of the night, it's not very valuable because everybody's sleeping, right? You're not using electricity. So you want wind areas where the wind is blowing in the evening when you actually need a lot of electricity. Water availability for solar plants, and what we call co-location, as in you can put your wind turbines, but also if the solar radiation is great, you can set up a bunch of solar panels in between the wind plants, the wind turbines, because that area is not being used for anything else, right? It can be used for farming, it can be used for grazing, but that's just one more way for the project developer to earn more money by setting up both solar and wind at the same place. So we have developed these tools, these maps, and you can go to these websites and actually see. Do you mind if I just go and check it out? Do you guys want to see some maps?
Yes.
Yeah, okay. All right. Let's see how good your internet is. Ah, there it is. Okay, so it's called MAP-RE, Multi-Criteria Assessment for Planning Renewable Energy. Lots of words, but don't worry about those. I'm going to go to our latest project. It's called Low Carbon Transitions in Southern Africa. If I yawn, it's because I just got back from Namibia less than a week ago, so it's like 3 a.m. in the morning there. We had a workshop to basically show all these results. So if you scroll down, there's a bunch of results from our recent paper. We basically create open source data for people to just download and use. So everything is free and open source. We have a zone mapping tool. If you go to the map all the way to the bottom, you can select what's your favorite Southern African country. Tanzania? All right, let's go here. South Africa is the obvious one, right? Everybody wants to go to South Africa. Okay, so if I go to Tanzania, so this is the most suitable, these are the most suitable wind sites that we mapped. The more red it is, the better those sites are. So if you look at the legend on the left, you will see for red, it's the lowest numbers, which means it's the lowest cost. Okay, it's dollars per what we call megawatt hour. Megawatt hour is a unit of electricity generation. Okay, so Tanzania is this big, but you can then see that wind is just focused here on the east side. And if you click on any of these, you'll see on the right-hand side there's how much potential there is, what is the distance to nearest road or transmission, and what's the levelized cost of generation. You can change it to solar, and then you will see where the solar resources are as well. Okay. So there's more to it. You can go back and look at the Tableau tool here, where we see a lot of different renewable energy zones, right, for different areas. So it's just a planning tool for planners to decide where to extend their transmission lines and build more projects, okay? And based on this analysis, our tools, we collaborated with the World Bank. Do you guys know what the World Bank is? The World Bank. Yeah? Okay. So the World Bank is, a bunch of countries have shares in it and they give loans for projects, right? But they also do these kind of cool tools for planning and assessing loans for renewable energy projects or even fossil fuels. So they made this tool which can map wind and solar resources across any part of the world, which is really cool. I think the internet is a little slow, so okay. Any particular country with I need to choose a small one so we can demonstrate this. Let's see. Barbados? Why not? Okay, I've never actually checked this one. So you can click, let's say if there's any onshore wind. Let's click on these. This is done. So what this one does is, again, create zones. The same thing that we did, but it does it all in real time, like in your browser. So I'm going to generate renewable energy zones here. And unfortunately, Barbados doesn't have any wind resources. Bad example. Maybe it has solar. Let's try solar. Okay, so it has a bunch of different solar resources right here. And you can explore basically any country in this particular tool. Okay? Questions? Yeah.
Where do they get this real-time information from?
So the information is not real time, the processing is real time.
Okay.
So all the data is already there. The data behind these maps, it comes from these solar and wind resource maps from the World Bank themselves. And then there's a whole bunch of, the sandwich layers that I talked about. All those data is basically baked into this tool. But the real-time processing in your browser happens after you give a whole bunch of impacts, whole bunch of inputs for cost or just these different criteria, how far you want it from a transmission line, etc. You can apply these filters. So all that processing happens real time. Yeah.
So is the analysis of these kinds of maps, trying to find those optimal zones, something that either is or can be done by like artificial intelligence to sort of make the process more efficient?
I haven't really thought about how you might apply artificial intelligence here, because it's a spatial analysis. The date. So, do you have something in mind that?
No, I was just wondering like how it is that, I guess it's just be more, you don't really need AI.
You don't really need AI for this. Yeah.
Yeah.
AI, or I should say like machine learning, you just need a lot of data to, we have used machine learning techniques for looking at what the propensity of development of these zones are, okay? So this particular analysis, is the first step. It's a static analysis. We've looked at historical data on how wind speeds and solar radiation is across these regions over, let's say, 20 years. That's what these are average 20-year data. But then the amount of suitable areas is so vast that it's still pretty much open for project developers to then choose, even after applying all these constraints and restrictions. So then, how do we know where project developers might go? So we can look at historical behavior patterns, right? So there are certain factors that project developers may value that we are not capturing in this analysis. Okay? So in that case, what we did for the US recently was that we had these suitability maps, okay? These are called site suitability maps. And then we looked at the pattern of development of actual wind and solar projects, and then use machine learning techniques to then project how project developers might develop given their past behavior. So that's how machine learning could come into play.
Thank you.
Yeah. Other questions? Yeah.
Does your lab work, is it working with the project in Norway with offshore wind energy?
Oh, so the question is, is my lab working on the offshore wind project off of Morro Bay? So we haven't directly. One of my students has looked into that, but we don't have like an official project yet. Although my colleagues are right now looking at offshore wind in that area to see how they could act like conservation zones. So if you have offshore wind projects, then you're not going to allow fishing in that area, right? So these are called marine protected areas that we already have off of Santa Barbara coast as well as the wider California coast. If you restrict fishing in certain areas, the spillover effects of those marine protected areas is shown to be really high. So which means fish are able to reproduce, and then those fish spill out in areas where fishermen can actually go. or fishers can go. And that study is going on. My colleague has also looked at the best offshore sites. So off of Morro Bay, I mean, the area is huge, right? But you still want to see where the best sites are, how far they are from ports and whatnot. So we are sort of moving in that direction. Other questions? Okay. How are we doing on time?
Getting close to 4:30, but you still have plenty of time.
Okay, cool. Great, we haven't started talking about the research projects yet. So this moves on.
I think your time on there might be different than I watch you.
Oh,
I was looking at that.
I'm at 4:05.
Okay, yeah.
Is that
I'm
right?
at 4:03.
Okay,
We're about
that's close.
halfway.
Okay, cool. So the other challenge that we are working on is the increased variability and uncertainty due to wind and solar generation. As I said, they're weather dependent. We can forecast wind and solar, how much they're going to generate, 24 hours from now, maybe even a week from now. The forecast errors change, but it's still going to be variable. And you always need electricity. So supply always need to equal demand. When you wake up in the morning, you turn on your lights, your demand starts growing, not just yours, but entire California's. You turn on your toasters, coffee makers, your demand starts growing, and then everybody's at work, going to college. But then in the evening, you're again turning on the lights, your televisions, and the load, climbs even higher. So it oftentimes peaks in the evening. If it's a really hot day, you might have a lot of air conditioning in the middle of the day. But then at night, everybody's going to sleep, not using much electricity, so your demand is constantly changing. But on the other side of that transmission line, somebody's always putting a little bit of more gas or turning it down, right? Putting in some more coal or some nuclear heat. So your supply always has to equal demand. But when you put wind and solar in the mix, the rest of the generation sources, which we call dispatchable sources, as in you can control them, they have to balance the grid, okay? So how do we manage that system and then plan out our system such that our entire system is going to be reliable? We're always going to have reliable electricity supply. So that's the challenge that we have here. So for that, what we did is we have created this open source, what we call optimization model. What's an optimization model? It is a model that takes in a whole bunch of inputs, and then you have a whole bunch of constraints. For example, this transmission line can allow only X amount of electricity to pass over it. This particular power plant is going to, at most, generate this amount of electricity. This particular power plant is not going to operate below a certain level because it might have to shut down. These wind power plants are always going to have this kind of variable generation. So you have all these constraints built into the model, and then you're also giving it a lot of costs. So how much would this particular plant cost to generate, to invest in, etc. And then the objective function, what we call, is to minimize the cost of your entire system. Now, why do you want to minimize cost? Because who's paying for this electricity? Us, right? So we always want to build an electricity system that is the most cost effective, so our electricity rates are limited, okay? They don't rise at a crazy rate. So that's the optimization model. These models, can run on your laptop, but they get complicated pretty quickly. So then we have to run it on a supercomputer. So most of our models that we run now are on supercomputers, but you can have a simplified model that can run on your laptop as well. So this model, we call it grid path. What it does is it's a planning model, that's how we are using it, where we want to know what kind of infrastructure investments we want to do in the future. What kind of power plants we want to invest in, what kind of technologies, what kind of transmission lines, where do we want to lay more transmission lines, what kind of battery storage we want to invest in, how much we want to invest in that, to meet future demand that we are projecting. Okay, that's what comes out of the model. So it optimizes from today all the way until 2040 or 2050, like a future year. So that gives us an idea of how our electricity system is going to evolve. And it takes a lot of inputs like existing generators and transmission, what potential generators, storage and transmission assets you might want to invest in, what kind of wind and solar resources or hydro resources are available to the model, and then of course future demand, future electricity demand, how it's going to evolve. Because it's going to change, right? It's going to grow, or it might stay the same. But if you all electrify our transportation, use a lot of EVs, our electricity demand is also going to grow. We have to project how you're going to charge your EVs. When are you going to charge them? In the evening at home? Or are you going to charge at your workplace? How many chargers are there? Are we going to be able to do that? So all these factors come into play. So it gets pretty challenging, right? You can see all the different components of this. So we try to do different scenarios. But what comes out of these models is, of course, these new generator, storage, and transmission assets that we want to invest in, and then the costs, but also the emissions, both global and local emissions. Okay? So GHG emissions, carbon emissions, and local emissions like particulates, which basically create, give you asthma and respiratory diseases, heart diseases. Because we want to see, our different pathways on how we're going to decarbonize, what are the impacts going to be on global and local emissions. Okay, I'm going to pause here before I hit those two projects that I'm going to talk about. Questions? Okay. So the first project I'm going to talk about is this project based in Southern Africa. That's the map of Southern Africa. You have 12 countries in mainland Southern Africa. There are also Madagascar and some other islands, Seychelles and Mauritius, but we don't look at that. We're looking at this particular region. 9 out of these countries are interconnected with transmission lines. 3 of them are going to be connected pretty soon. And it's a pretty unique region. One, because it has a lot of areas that have high biodiversity value. Endangered species, flora, fauna, it's an amazing place. And there's a lot of potential for large hydropower, as well as coal. So South Africa actually has the most coal generation on the African continent. It's the 14th largest GHG emitter in the world. But then other places like Democratic Republic of Congo, the Congo River, it's ends right here at this little region that hits the, is that the Atlantic? Do you guys know the Three Gorges Dam? Who's heard of the Three Gorges hydropower dam? Anybody? Yeah, it's the massive dam in China, right? It's the biggest dam. Its size is about what we call 23 gigawatts. The potential for hydropower just in this part of Congo is double that size. Okay, so huge potential. Does it mean that we build it? We argue not, because there's a lot of biodiversity value in that particular river. There are not that many hydropower dams here. But the river is so wide that in some places, one particular fish species has evolved differently on 2 different banks of the river. Okay. This river also deposits a lot of carbon into the ocean, and that's a pretty big carbon sink. So there's a lot of biodiversity value, and it's also going to displace a lot of people, right? So there are lots of sites, planned hydropower projects here that we wanted to question. And of course, there's a lot of potential for wind and solar, and demand is expected to double by 2040. So growing region. So our research question was that, can wind and solar play a significant role in Southern Africa's electricity future? And then what would the impact be on plant infrastructure costs and GHG emissions? Okay. So this will just give you a flavor of what we do, how do we answer these questions. So you don't have to understand all the data, the numbers behind it, but I'm going to give you the high-level messages on what these modeling exercises can provide you. So we mapped all the existing generators, and so these pie charts are basically shares of different technologies. So you will see a lot of blue, and the blue just means a lot of hydropower, okay? And then there's black here, that's a lot of coal in South Africa. Now these pies, these circles, these pie charts, they're not scaled with size. So if I scale it with size or by size, the pie in South Africa will just, it's enormous. And then these, of course, these are all transmission lines. And then on the right-hand side, these are all existing and planned hydropower. So remember I told you about these, the Inga Dam is the name of this proposed dam here. And there are 3 different dams. That's why you see these big circles, but there are 3 of them. So adding up all that becomes a really large hydropower potential. So we mapped all this stuff, and then also the solar and wind resources, and then put it in that optimization model. And what came out of it is what kind of infrastructure we want to invest in. And you will see we have results for 7 different scenarios going from 2020, 2025, 2030, 2035, and 2040. So lots of bar plots, right? And all these different colors correspond to different technologies. These hashed bars are all existing generators. And then this gray, black is coal, gray is gas, dark blue is hydro, orange is solar, light blue is wind, and this ochre color is battery storage. So let's just look at 2040, okay, just the future. So what do we learn from here? If you look at these plots, there are, of course, 7 different scenarios. One is we assume that wind and solar costs are just not going to change, but it's unrealistic. They are coming down, we know that. We had a couple of scenarios where we didn't plan or build new transmission lines. We had a reference scenario. Then we had a couple of scenarios where we retire existing coal-fired power plants early. And then the last scenario just imposes an 80% clean energy target. California has these clean energy targets. Have you heard of those? It's called RPS, Renewable Portfolio Standards. We have these targets which says that by, by 2030, we have to reach, I think, 60% renewable energy. Okay, and then everybody, starts to sort of build more wind and solar or other clean. It's mainly wind and solar here in California to meet that target. So we impose that target in Southern Africa as well. So one insight was that wind and solar is going to dominate in 2040, even without any targets, like just based on costs. You will see, look at the orange and light blue bars, right? It's a pretty big chunk. Right? This is within 20 years, this could potentially dominate, and you don't need that much hydro or gas-fired power generation. So that's pretty promising, right? Because you can't really expect developing countries to do a lot of wind and solar if it's going to cost them more. It's unfair, right? They have not been responsible for historical climate change, so their responsibility has been lower. So we can't really expect them to do that. But if the most cost-optimal solution is, telling you that wind and solar is a promising option, then why not do it? We also found that no coal was built across any of these scenarios unless you completely restrict transmission lines. So all those planned coal-fired power plants in South Africa, they should basically stop now. Doesn't make sense. Which is great, because coal is like by far the worst polluting machinery in the world, okay? So we had to basically stop coal. And then the last major insight was that at most half the hydropower projects was built, the planned projects. As I said, hydropower projects have their negative impacts. They displace population, they flood a lot of areas, a lot of them are close to protected areas. So you want to try and avoid them as much as possible. But of course, you can't tell developing countries to do so if it's going to be cheap hydropower plants, but they're not cheap, okay? They're super expensive.
I have a question.
Yeah,
Given the current efficiency of solar panels on farms and like batteries and stuff, how realistic is it to supply 60% of our energy via those like clean energy solutions?
yeah, great question.
Is this assuming that they're going to become way more efficient in the future?
Yeah, great question. So I'll repeat that. So the question is, given the current efficiencies of wind and solar, is it realistic to expect 50, 60% of our energy coming from wind and solar? Have we even included that? Do we expect efficiencies to go up? So there's a difference between efficiency and cost. Okay, efficiencies influence costs, but it's not the end all be all of costs. And what really matters is costs. What is the dollars per megawatt hour considering the efficiencies that we have today? So we are looking at all these numbers based on current efficiencies, currently achieved efficiencies. So all that is baked in this analysis. Now, as efficiencies get better, costs are going to come down. We have sort of taken that into account as costs come down. That's how these results, are what they are. But essentially, the costs themselves are so low. They're much lower than coal and natural gas right now. It's just the intermittency that is that increases the overall cost of the system. That's why we need that battery storage to balance that wind and solar. But we look at all of that. We look at how solar generation is going to change across the days. At night, we're not going to get solar generation. Then what else is going to be required during those times? All that is baked into this model. And California's, again, all those targets are based on these particular studies. But great question. Other questions?
A little bit more part of my question was I was curious about, earlier you were saying how much space or area we need in order to house these solar units.
Yeah.
Is that, I guess you're including that as.
Yeah, so the question is, do we have enough space for wind and solar because they occupy so much space? So we do, and even that is also baked into this analysis. So the solar and wind maps that I showed you, we looked at that whole sandwich of spatial data sets. We removed all the protected areas, all the high biodiversity value areas, all the places, cities and urban places, water bodies, etc. And those maps were just the remaining land. And even that is at least 5 to 10 times what you would actually need to meet these targets. Yeah. Even in the US, we have the same situation. We have a lot of land here. And that's why it's so important to go to just those places that have the least other impacts that we don't account for, like biodiversity value and all those things. We need to account for that. Otherwise, the potential is vast. Yeah, we're not limited by potential. Yeah.
Does the 60% include private residents own solar powers or own solar panels as well?
It does for California, right?
Yeah.
Yeah, it does. Yeah. Okay. So that's just the potential, right? Or that's just the infrastructure investments. We also looked at the costs. So these two plots on the left-hand side are costs on the y-axis, GHG emissions on the y-axis on the right. So you will see costs are sort of going up. We haven't included existing costs, so I want you to focus just on the differences in costs here. And they're all bunched together here. So costs don't really increase that much across scenarios, but emissions are quite different. Okay, these are the emissions trajectories. So the one insight that we got here is that just looking at the reference scenario, the most likely scenario, the emissions trajectory is this black line, okay? And what we found that if Southern Africa invests according to this optimal plan, the emissions in 2040 will be very similar to 2020. So even without, putting in more carbon targets like how California does, Southern Africa could basically freeze their emissions at 2020 levels, which is a great first step, right? Now, because GHG emissions is a global problem, right? It doesn't matter where your CO2 emissions are coming from, whether it's Southern Africa or California, they're all going to affect us all the same, okay? CO2 emissions don't have impacts directly on our health. It's not like air pollution. It's, you want to mitigate it in any part of the world, it's going to have the same benefits and the same impacts. So if we decide to impose an 80% clean energy target on Southern Africa, then the costs increase only by 6%. Now, why is it important to quantify this? Is because maybe the international community steps up and says that, hey, we should invest in clean energy in Southern Africa because we can get more bang for the buck, right? And then we don't have to impose those costs on Southern African consumers because they were not historically responsible for climate change. you see the logic behind this? So this is, I mean, this is global environmental justice right here. Okay. All right, questions before I move on to the next, we're really close to ending. Should I'll quickly share with the next project, but let's take questions, yeah.
And the return on the investment for future clean energy solutions in like South Africa, for instance, makes sense, but that doesn't solve the world's largest polluters who are also growing. Their consumption rates are growing at an increased rate. So how do you deal with China and the U.S. and some of the larger polluters who already have infrastructure in place, but could be interested in repurposing that infrastructure towards more clean energy solutions?
Yeah, that's a great question. So this particular project, so the question is, what do we do with the largest polluters like China, US, and now India is also building a lot of coal? What do we do with those particular countries? How do we convince them to reduce those emissions or retire their coal-fired power plants earlier or their natural gas ones? So this particular project is just showing Southern Africa, growing region. You can avoid building new power plants. We also have a project both in India and China. My colleagues work in the US electricity sector. I'm going to show you an example of the transportation sector in the US. But even these countries have, they're installing a lot of wind and solar. Like both India and China is of course installing by far like the most solar and wind right now, like almost double than the US. At an enormous pace. But they're also building new coal plants. So it's a whole different scale. And what we are seeing though in our transitions scenarios is that even their cost optimal scenarios, early coal retirement just makes sense. So there are policies in place. People are trying to pursue those. It's of course harder to convince them, but their internal sort of plans are also to slow down those emissions. But we use similar models to do that. One of my students is from mainland China, and he's working on that. And the results are promising. The question is all about implementation policies. But it's in China's interest to actually reduce their emissions. Yeah, so we'll see how that evolves. Okay, maybe I'll just verbally talk a little bit about the last couple of projects before wrapping up, if that's okay, and I won't show you more data. But here's just one. So this other project is about decarbonizing California's extraction and refining sectors. Okay. Do you guys know where this picture might be taken? On the left. Who's from LA? Sorry to put you on the spot, but it's LA, right? Have you guys been to LA and seen such oil wells or no? There are a whole bunch of oil wells in LA's neighborhoods, okay? And then of course refineries, right? We have refinery clusters in the Bay Area as well as the LA area. And if anybody's been next to refineries, they smell, right? They're terrible. But we need those for our fossil fuel cars. If we all convert our cars into EVs, you don't have that problem. So, to meet California's decarbonization targets, which is I think we have carbon neutrality by 2045. Okay, pretty ambitious target. That's this project. Like, we wanted to see what the impacts are of those decarbonization targets, what kind of policies might we need to phase out oil extraction and refining. But to give you a sense, this is California's map. The areas in red, they're all oil fields, okay? And these are the 5 largest counties in red border that are oil producers. And these orange areas are what we call disadvantaged communities. Has anybody heard of disadvantaged communities, this term? Yeah, right? So California has designated certain communities as disadvantaged because they have historically borne a disproportionate burden of air pollution and other pollution, okay? So these are what we call census tracts areas that are considered disadvantaged communities. So we wanted to see how these decarbonization policies would affect disadvantaged communities versus others. And then you will see these green dots. These are all refineries. They're all clustered in the Bay Area as well as LA, and then some in Kern County. Now, fun facts, only 0.9 or 1% of California's GDP comes from the oil sector, but 11% of greenhouse gas emissions come from extraction and refining. Extraction is about 4%, refining is about 7%. So pretty significant. But 23% of criteria air pollutants come from this sector. These are the pollutants that basically affect your health. 26% of toxic air contaminants come from this sector, but is responsible for providing employment to only 0.2% of our workforce. Okay, because it's then a debate between health and jobs, right? So what we wanted to see was how would these decarbonization policies affect air pollution exposure, but also employment in the oil extraction sector. So you will notice that most of the oil extraction happens in this region, and employment is mainly in Kern County, right? So then, I have a whole bunch of course, charts, but I'm going to just tell you verbally in the interest of time. We are at time almost, right? Can I take just a minute? Okay, so what we saw, we looked at 3 different policies, okay? One was what we call setbacks. Setbacks is just how far you can have a home or a school from an oil well, okay? And what that says is if a setback is 2,500 feet, then you cannot have a home or a school or other what we call sensitive receptors within those 2,500 feet from a well. So you have to retire all those wells, existing wells, and then not allow new wells to come close to these homes, because the closer you are, the more exposed you are. So that was one policy. Another one, we imposed a carbon tax on oil extraction, and then the third one was excise tax, as in it's a tax on just per barrel of oil. And then we had different levels of stringency for each of these policies, and then looked at how quickly the production of oil will be phased out by 2045. And then from that, we looked at how would health outcomes change for communities across California, both DACs, disadvantaged communities and not. And then how would employment change across counties? And then we quantified that. And then looked at what we call equity impacts, as in, are the benefits of health going more to disadvantaged communities or other communities? How's that evolving? Are jobs being affected more in disadvantaged communities or not? So that was sort of our study. And we found that setbacks is one of the most effective policies we can implement to get the most equity, the best equity outcomes, and also the best health outcomes. Okay. And then I was going to show a third project, which is in India, where we wanted to, or we are looking at how to incentivize low-income households to buy more energy efficient appliances, because they can save money, and from a demand perspective, we can reduce our overall demand, which means there's less coal generation, less polluting generation. And that we had a big field experiment to look at how much people might pay for these fans. So that's a completely different type of research that we do. It's completely a field experiment, not modeling. So those are sort of the flavors of the research projects that we do in our labs. So I'm willing to take more questions, but I know we are at time, so I'll let Amanda.
Well, maybe we'll have one question, and then if you have more questions, you can come up and talk to your So maybe one question before we end?
No pressure.
Maybe
I have
everybody.
another question. I'm curious, wind and solar are like pretty decent clean energy solutions, but is there any research being done to try and come up with different solutions for clean energy, or is that something you know about?
Research on other technologies?
Like, yeah, other technologies.
Yeah, there is definitely, so the question is, wind and solar, of course, is well developed. These are big industries, costs are coming down, but is there research in other technologies that is happening? So definitely there's a lot of research happening in, of course, offshore wind is now the next big thing. But there's research happening in wave generation technologies. Geothermal is probably going to be the next big thing, I feel. And the reason being that, do you guys know what geothermal energy is? Right? You want to tap into the ground and get that heat, make steam, and run a turbine, right? Most of our electricity generation basically happens that way. We create steam and spin a turbine, and then that spins a generator and makes electricity. But we don't have that many places to put our geothermal power plants. We only put it where we have hot springs and the lava or the Earth's crust is really close to the surface of the Earth. But new technologies that were actually developed for drilling oil, because we started going deeper and deeper into the ground, are now enabling us to reach the heat source that is well below the surface of the Earth. So if we can tap into those heat sources, then we can have geothermal energy in many more locations than what we have today. So that research is definitely really promising. There's some tidal energy research, but that's very limited, I would say, in terms of sites. But yeah, there's some happening. But having said that, wind and solar and geothermal now are at such a cost, such a low level of cost, that we have these commercial technologies that can help us completely decarbonize. So we should keep investing in these new technologies, but not wait for the silver bullet. We already have all the technologies that we need at a cost that we need. So it's promising. It's just a question of implementation and policies.
Thank you so much.
Thank you. Thank you.